number of words that have that term. That has some interesting properties. First, well, the main interesting property is that it makes common terms invisible, things that always happen invisible. If every word has a term, that ratio is 1, its log is 0, and it doesn't matter. I'd also like to call out that that's a function of all the words that you've ever seen. The TF part is a function of just a particular word under consideration, and the TF part of a term is the relative frequency of that term in the vector that you have. So there's an example below. If we have the observations V, D, H, I, Y, and we're using up to a 2-phone terms, then we have 3 terms in here, DH, IY, and DH, IYB, and each of those is 1/3, so there's 0.33 there, and for example, AA doesn't occur, so it's got a 0. I've made up some IDF values for those terms in the next column, and then if you multiply them together, you would get the TF-IDF weights for each of those terms, and turn that into the vector for that observation, which you see on the right. Okay, where do these TF-IDF exemplars come from? There's 2 basic sources of them. One of them is a linguistic dictionary. If you have a dictionary, you can take that dictionary, compute the counts, and for each word, compute its TF-IDF vector and use that as the exemplar for that word. The second thing you can do is you can use an empirical dictionary. You can do an unconstrained phonetic decoding and then take a forced alignment of the data and find where the boundaries are and what the actual realized pronunciations of the words are, and use that as a basis for creating the TF-IDF exemplars. In this work, we're using the third method, which is a combination dictionary, where we assume a back-off count of 1 occurrence of every dictionary pronunciation, and then add the empirical pronunciations. And that's what's going to let us learn unanticipated pronunciations. And it's sort of interesting that as you do this, the IDF part is automatically going to downweight common garbage that just gets decoded all over the place. Here's an example of some observed pronunciations, just to make this a little bit more concrete. These are observations of the word Blake in a voice search application. The first column is the word itself. The second is the expected pronunciation based on the dictionary. In this case, we just have 1 pronunciation of Blake, so there's no difference there. The third column is the count, and the fourth column is the observed realization. And so it turns out that for the actual phoneme decoder that we used here, it's a little bit more likely when Blake occurs as a word to actually decode it as Plake instead of Blake, and that's now being captured when we create the TF-IDF vectors. Okay, so the acoustic score that we have so far that we're going to use in the decoder, this acoustic score relates a word to a segment, and that's given by the dot product of the TF-IDF vector for the word